Can we start now?
Yeah.
Yeah, we can. Maybe you are waiting somebody has to come, or then we can start.
No, we are not waiting. Okay, so good morning, everyone, and welcome. Today we have Professor K. Somasundaram from Amrita Vishwa Vidyapeetham, Coimbatore, India, and he will be talking on combinatorial matrix theory, conjectures on permanence. So the slides of today's talk are also available on our web page. So if you want to access these slides, you can also download from our web page. And yeah, now you can start, sir.
Okay. On outside, I thank the organizers for having a wonderful webinar series. Am I audible? Okay. Yeah. So I thank the organizer for having a nice opportunity to talk some of my recent results on conjectures on permanence. Okay. The first few slides are very basic things. Okay, please pardon me if you know already. Okay, I'll talk about the permanence and then development of permanence and other things. Then okay. This work was jointly with Professor Maria Rudraj, Professor Subramaniam, and my recent scholar Divya K. Okay. So. Okay, this is this slide. I just overall view. We'll talk about what is meant by a generalized matrix function. Then we'll talk about the permanent. What is a permanent? Then we'll talk about the permanence and graphs. Okay, not this slide. Then the two conjectures on that. One is a permanent dominant conjecture and Lie-wang conjecture. If time permits, I'll just talk about the other important conjectures in line with the Lie-wang on. This is the schedule. Okay. If you take a complex group algebra of C of Sn, Sn is Sn is a symmetric group on n elements at 1 to n. Okay. Then I take an element lambda from the C of Sn, the group algebra, okay. And then I define the function f lambda of A equal to summation lambda of sigma product of AI sigma I, the sigma over the subgroup of this Sn. Okay. This we call as a function. If you specifically take this as lambda as a character of this subgroup H. Okay. I take A is an n by n matrix, H is a subgroup of Sn, and X is a character of the subgroup H. Then we define f chi of A is summation over sigma belong to H, chi of sigma product of AI sigma I. This we call as a generalized matrix function. Okay. This is a well-known function when we start learning about the determinants and other things. Okay, this is the beginning of the determinant. Okay. This is a generalized matrix function. This generalized matrix function comes from the basic of a complex group algebra. Okay. 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 Let me specific on that. Okay. If you take G as instead of any G, if you take G as Sn and chi is irreducible, okay. If chi is irreducible, then this f chi, the f chi which we define in 2, is be called as an imminent function. It is called the imminent function. Okay. This is a very famous one. So this chi can be taken on different ways on that. If you take chi as chi of sigma is always 1 for every sigma, for every permutation, this chi of sigma is 1, then we call it as a trivial character. The alternating character means that chi of sigma is 1 if sigma is even, and chi of sigma is -1, then sigma is odd permutation. So when I taken sigma is an even permutation, then I assign chi of sigma is 1. If take odd permutation, then chi of sigma is -1. Such a character we call as alternating character because the sign comes alternatively. Okay. Now, based on this, there are two things on that well-known one. If you take your chi as a trivial character, okay, that means chi of sigma is always 1. Then the generalized matrix function or the imminent becomes a permanent. Okay, so the formal way of definition permanent of A is summation over A1 sigma 1, A2 sigma 1, etc. AN. That means product of AI sigma A. In this case, I take chi of sigma is 1 and sigma is my S. If you take chi as an alternative character, take chi is an alternative character, then this imminent function, okay, becomes a determinant. It's a well-known definition for us. Okay, summation over sigma is a -1 whole power sign of then AI sigma I and other things. Okay, there's a slight difference between permanent and determinant. You take as chi as a trivial character, your imminent becomes permanent. If you take chi as an alternative character, then it becomes determinant. If you take chi equal to 1, chi of E equal to 1, where E is identity permutation, and chi of sigma equal to 0 for all other case, then the generalized matrix function becomes a Hadamard function. Okay, it's a well-known Hadamard function. We do from that we have a Hadamard product and other goes with. Okay, the definition of generalized Hadamard product which comes here. So there are three things based on the chi which we are doing. Okay, I'm concentrating only on the first part of permanent on that. Okay, that's what this talk is talk about the conjectures on permanent of A because determinant we know that. Okay, we know the determinant and permanent are slightly different on that. Okay, it's only on a trivial character, otherwise an alternating character. But computationally, both are extreme on that. We know that Gauss elimination method gives a fast algorithm for finding a determinant. Okay, mostly on a polynomial time. But permanent is not that. Okay, it's highly complex. Valiant has proved that this permanent is a sharply complete on that. Okay. This is one of the class of sharply complete problems. Okay. So you don't have a polynomial time algorithm for. Okay, there are some simple cases where people start looking the polynomial. Even for a 0-1 matrix, there's no polynomial time algorithm for the permanent function on that. Okay, so when this concept of introduce it, okay, Polya is looking that is can you take permanent as a transformation of a determinant. Okay, this was initially okay, because these two are look like a twin problems on that. Okay, just changing the character only from alternative character to a trivial character. So Polya is proposed that is there any such a transformation on that? Permanent can be written as a transformation of a determinant. Okay. In 1930, and the same year Sergio shows that you cannot have such a transformation, or you cannot generalize it for n greater than or equal to 2. Sorry, n greater than 2. N equal to 2 is of course I have shown permanent of x11, x12, x21, x21 and x22. Sorry, that is x22. Is same as just to change the sign you will get it. But in this case of n equal to 3 and more, such a transformation is not exist. This was also proved by Marcus and Mink in 1961. You cannot have certain permanent determinant functions on by a linear mapping. Just simple linear mapping. You cannot take determinant in terms of permanent or permanent in terms of determinant. Okay, so that means the permanent goes in a different line. Okay, you cannot take all the results of a determinant in terms of permanent. Okay, you cannot generalize the determinant result into the permanent one. Okay, that's the main focus of this talk on that. Okay, I show you how this one result is easy. It cannot be solved on it. For example, solving a system of equation through determinant is quite easy. People start looking solving a system of equation through determinant, the permanent. It's a bit difficult on that. Then people looking on this permanent in terms of graphs. Okay, I just introduce it. I'm not going to a deeper part on this. Okay, if you look this permanent, as I mentioned that permanent is if you look this definition, this is basically A11 sigma 1, A12 sigma 2, AN sigma n. This we call as a diagonal product. It's sum of a diagonal product. So permanent we can look as a sum of diagonal product. So if you look the corresponding adjacency matrix, what happened to the diagonal product? This diagonal product gives either one factors or one factor and cycle, or as a full cycle like a Hamiltonian cycle. Okay, so you take the adjacency matrix of a graph and then try to find this one factor, what happened to the corresponding graph. Either this one factor still is a full cycle or a partly a cycle with the one factors or different one factor. Okay, so people start looking on how many one factors on that, what are the relations between that, what are the bounds of that. Okay, so these are all the simple results on that. Permanent of a complete adjacency matrix of a complete graph is a n factorial. This was proved by Ming, okay, around 1968. It's using an induction. And if T is a tree, then the x of T is an incident matrix, then x dash of T is n. Okay, T is a tree with n result. This is also proved by an induction, and these are the few easy observations. Okay, these very trivial observations on that. So the first one looking on in terms of factors is Harare. Harare looks the permanent and graphs and try to find the number of one factors in terms of permanent. Okay. Later, so many people start counting the one factors for the bipartite graph and other graphs. Yes.
Sorry, I lost a little bit. Can you please define what is one factor again? One factor.
One factors.
Yes.
One factor is a graph which has you have a collection of subgraphs with the edges on them. Okay, the degree of every vertex is. I call it as a perfect matching. In the case of even number of vertices, we will have a perfect matching.
Okay.
So I'm not using the word perfect matching because you may have a graph with the odd number of vertices and even number of vertices.
Okay, so one factor is collection of subgraphs, is it?
Yeah, it's a collection of subgraphs with a single edge on. The usual Harare definition, Harare harvested.
Oh, okay. Sorry, I haven't. This definition is very much new to me. That's why. Okay.
Yeah. Two graphs, two factors are it's a cycle. Degree of that it's.
Okay.
Okay. So what happened? Diagonal product in permanence gives either a full cycle or some two factors and one factor, or it's like a one factor. Okay, I'm not using the perfect matching, okay, because perfect matching goes when the graph G is number of vertices in even. So later after Harare, people start looking. I just highlighted only few results. Okay, particularly Boroldi and others. They try to enumerate the one factors in terms of the Laplacian of G, okay, in terms of degree also there. Okay. So some of the few results on that. Habal is trying to prove the Pugh's theorem using the permanent on that. Okay. So a few results on that. Okay, now I'm coming to the major part of my session. Okay, it's called a permanent dominant conjecture. I hope everyone knows what is van der Waals conjecture. Later it was proved. Now it's called the van der Waals theorem. Okay, this is based on the doubly stochastic matrix. Doubly stochastic matrix is a matrix where the row sum and column sums are 1. The stochastic matrix. We know that. Okay, so row sum and column sums are 1. The entries are between 0 and 1. Okay, so xi's are 0 less than or equal to xi less than or equal to 1 are these entries, and then the sum of the rows and sum of the columns are 1. That's what's called a doubly stochastic. If the row sums are 1, we call row stochastic or simply a stochastic matrix, okay, as we discussed in statistics. So van der Waals has proposed a conjecture that what will be the minimum permanent value of any double stochastic matrix. He conjectured that it is n factorial by n power n. N factorial by n power n is less than or equal to permanent of A, where A is any double stochastic. This is a well-known van der Waals conjecture. Later it was proved by Edwards and Flickman and independently. So it becomes a van der Waals theorem. Okay. Now, after this van der Waals conjecture, the second one is the permanent dominant conjecture. Permanent dominant conjecture is one of the well-known conjecture in linear algebra. It was proposed in mid 1960s. Okay. Still, this conjecture is open on that. Okay. This is one of the top conjectures in linear algebra. Okay, this conjecture is proposed by this way. Okay, as I told that people start looking the development and results of determinant through this permanent. So, sure prove that determinant of A, I'm taking H as Hn is a set of our positive semi-definite Hermitian matrices. So, you take A belonging to Hn, okay, and find the determinant. Determinant is f chi of A by the chi of In. He proved this result. Later, people start looking that is it possible to extend this result to the permanent. Okay. Okay. So it cannot be permanent less than or equal to that because permanent is the maximum value. So people start looking on the permanent of A is greater than or equal to f chi of A by chi dot 1. This is the motivation behind this permanent dominant conjecture. It means that the permanent is always dominate all the imminent functions. Okay. F chi of A by chi 1. Okay, it is like an average imminent function. So permanent is dominates on that. So this is what people start. Sorry. People start looking this for different cases. There are some simple cases on that. Okay, this is very evident. Okay, if you take a real non-negative matrices, it always satisfies the permanent dominant conjecture. For a trivial and alternating characters. For general, it is not true. General still it's not. I say it's not true. It still is open. But in case of a trivial and alternating character, the conjecture is true for real and non-negative matrices. Okay. But the conjecture is only for a positive semi-definite Hermitian. If you take A as a positive semi-definite matrix, and then specifically as a correlation matrix. Okay. When I say a correlation matrix, the diagonal entries are equal to 1. Then this permanent dominant conjecture is true in this case. Okay. These are all known result on that, more general. But generally it has a lot of attention in terms of a combinatorial aspect. That's the reason that I mentioned this title as a combinatorial. Okay. People instead of looking as a linear algebra aspect, they try to look into the combinatorial aspect on it. We see whether it's possible to solve this conjecture. Prove this conjecture by a combinatorial way. So we start with the result of Pate. Okay, Pate has contributed a lot in this one. I just highlighted that what are the existing results. In 1992, Pate has tried to solve this result on that. Okay, he defined a partial order on a set of partitions on N. Okay. We mean that lambda and mu are two such a partition, and chi dash are the characters associated with the lambda and mu. Okay. And both are irreducible characters on S. Okay. I mean that lambda is related to mu. Okay. It means that this imminent function is less than or equal to the other one. Okay. So f chi of A by chi 1 of n is less than or equal to f chi dash of A by chi dash of 1 of n for all Hermitian matrix A. Okay. So now people start looking what are the partitions which satisfies this. Okay. So the specialization of permanent dominant conjecture is nothing but you find a partition lambda satisfying this one. Okay. So the lambda is related to n. Is it possible to find all partitions which satisfies these conditions? Okay. So if you are able to find all such partitions, then the conjecture is true. So people start looking on different partitions and try to prove these conjectures. Okay, and a different aspect on. Okay, So behind this, there are some symmetric groups concept are there. They're defined, well defined on symmetric groups and hook partition. James in 1992 he proved that whether this, as I told, this inequality, whether this equality, the bound, the upper bound is a sharp or not. He gave an example. It's achieved the equality of the inequality. That means the bound is a sharp bound on. Okay, this. So if you take lambda as k times 1 power n k, it means k, then 1, 1, 1 on n minus k times. If you take lambda as a partition of n, and chi lambda is a character associated with the lambda, then I call chi lambda as a single hook imminent. Okay. So this conjecture is settled for the single hook element by Heffron. Heffron in 1988, he tried to prove the conjecture for this single hook element with this inequality. Later, James and Liebeck tried to prove the conjecture for the partition lambda of n that satisfies the specialization of permanent dominant conjecture. Lambda has at most 2 parts which exceed 1. Okay, you try to find a partition which with the 2 parts, okay, at most 2 parts which exceed 1 on that. Then Pate has improved this result. Okay, lambda satisfies the conjecture. It has exactly two parts on that. Okay, and Pate also improved his result by proving the following. He proved that if lambda satisfies the conjecture, if the following then, okay, at most 2 parts which exceed 2, at most 3 parts which exceed 2, at most 4 parts which exceed 2, provided the second and third parts are equal. In the case when we say, he tried to prove this by considering a specific inner product and specific partitions of a specific type of a partition. He defined a specific, the proof is slightly lengthy. It's very interesting proof. Okay. So he defined, for each case, he defined a separate inner product. And from this inner product, he tried to define a partition and then try to prove this conjecture. So in general, the conjecture was settled till n equal to 30. Okay, for all type of partitions, the permanent dominant conjecture is true when n equal to 30. Okay, all different partitions. So now people start looking on what happened to n equal to 14, 15, 16. Pate himself has tried for n equal to 14 and 15. He tried. He attempted only on that. Okay. For n equal to 14, he tried to prove that the 4 square and 3 square is the only partition which may not satisfy the conjecture. He gave it may not be satisfied on that. And for n equal to 15, 3 power 5, 5, 4, and 3 power 2 are the only partition which may not satisfy that. He is not sure whether it's not satisfied. He says that it may not be satisfied under this condition. So based on that, we try to extend the result of this n equal to 14. So we are interested on getting this conjecture for n equal to 14, 15, 16. So we got some partial result on this work was done by myself and my scholar Divya. We define a partition. Okay, we called as a derived partition. A partition obtained by adding a positive quantity. A partition obtained by adding a positive quantity to one of the parts of a partition, or to the right side of all the partition, or both. Okay, either you add to one part, or you add the right part, or both. In such a partition we call as a derived partition from the previous partition. Then we prove that if lambda is a partition on n, it cannot be derived from this 4 square, 3 square, and 3 power 5. then it satisfies the PDC. Okay, specialization of a permanent dominant conjecture. Okay. So this was proved. This was proved in general, but we have some examples on that. For example, if you take, I'm taking this partitions alpha as alpha 1, alpha 2, alpha t is a partition of n, and s is a positive integer such that alpha s is greater than alpha of s plus 1, and beta is another partition like this alpha 1 etc. alpha s minus 1 except alpha s. I'm skipping alpha s, alpha 1, alpha 2, alpha s minus 1, comma alpha s plus 1 and etc. 1. Okay. Then I defined the relation on this way. Then we prove that for n equal to 15, as I told, n equal to 14 onwards, this conjecture is true. N equal to 15, we prove that this partition satisfies the conjecture. Okay. Page has suggested that 4 square 3 square may not satisfy, but we proved that 4 power 3 and 3 satisfies the conjecture. Also 4 square 3 square 1, this also satisfies the conjecture. Slightly improved result of that. For n equal to 16, we obtained that 4 power 3 3 1 and 5 4 square 3 satisfies the conjecture based on the theorem which we have proved. Okay. Similarly, this 4 square 3 square 1 and then 5 comma 4 comma 3 square comma 1 also satisfies the conjecture for n equal to 15. Similarly, n equal to 15, these are the cases where the conjecture is true. Okay. 4 power 3 1 3 square, which dominates 4 square 3 square 1 2. Okay, like that. Since the partition on the left hand side satisfies the conjecture, the partition on the right hand side also satisfies the conjecture based on the theorem. Similarly, we have classified that these are the results we obtained for this permanent dominant conjectures for n equal to 15. Okay. So we slightly improved the result. We know that this conjecture, permanent dominant conjecture, is true for all n less than or equal to 13 and partially n equal to 14, 15. But we have tried to prove that certain cases in n equal to 15, 16, and 17. Still, you are looking that we try to generalize this for any n. Okay. It's slightly harder because you have to define each time. You have to define a certain partitions and then see that this partition satisfies this condition and verify whether the conjecture is true or not. So these are the major things recently we did on the partial dominant. But it's one of the very hardest problem in linear algebra, permanent dominant conjecture, which it requires not only a linear algebra, it requires some type of a symmetric group representation also is required on that. Through symmetric group representation only, I think we may be able to prove. For each case, we need to have a separate inner product. We have to define a separate inner product and apply some or different type of characters. Then we try to enumerate that or see that this partition satisfies the permanent dominant conjecture. Okay, this is my first result. Okay. The second conjecture which we are interested is called Lie-wang conjecture. It's very interesting. This Lie-wang conjecture also started similar to the determinant. Around 1960s, okay, E.T.H. Wang, he proposed this, whether such a inequality is true or not. Okay. You assume that let you take B as a W stochastic matrix. Okay. If permanent of TB plus 1 minus T times permanent of A is less than or equal to T into permanent of B plus 1 minus T into permanent of A, this inequality for all A belonging to the doubly stochastic matrix omega n. Omega n is set of all doubly stochastic matrix order n and for all T. Is it true or not? He was asking, and then he gave an example. I remember that this result was in American Mathematical Monthly around 1960. Okay. Later, Borolli in 65, he says that the inequality is not true in general. He gave an example. For example, Jn. Jn is a matrix where all the entries are 1 by n, 1 by n, 1 by n, 1 by n. Okay. Richard Borolli and Newman. Okay. Richard Borolli was a student of a Newman. Both have proved that the inequality, the Wang inequality, was not true when take Jn and okay, and then they try to prove whether this can be true for instead of 0 to 1, it is 1 by 2 to 1. Okay, they were asking. So this inequality parameter of Jn plus 1 minus lambda alpha into A of less than or equal to parameter of Jn plus 1 minus alpha. This inequality 6 is not always holds for 0 to 1. This was proved by Borolli. Later, Lee and Wang tried to look this conjecture and try to prove this result for this interval 1 by 2 to 1. Okay, for n equal to 3. And this, the post conjecture, this may be true for general n. They try to prove n equal to 3. And then they propose a conjecture that's called the Lie-wang conjecture. So Lie-wang conjecture is the inequality 6 is true for all A belonging to omega n and for all alpha belonging to the interval 0 to the 1 by 2 comma 1. Okay. So he tried to prove n equal to 3 and then he want to generalize it. Then he proposed a conjecture. This is one of the well-known conjectures on that, because this will talk about the convex combination of Jn and A. Why this Jn is important? Because Jn gives the minimizing matrix on that. Okay. According to the Van der Waals conjecture, the minimum value of the doubly stochastic matrix attained at Jn. So Jn is one type of a minimizing matrix. Jn is one type of a minimizing matrix. So people are interested on only on Jn on that. Okay. So what happened? The convex combination of Jn with the other doubly stochastic matrix, whether this inequality is true or not. So Lee and Wang have proposed this as a conjecture. So we are interested on he tried to do this inequality for n equal to 4. He is not proved for the general one, even though the conjecture is true for the interval 1 by 2 to 1. He tried to prove for n equal to 4 in the interval 0.63 to 1. This is a big expression. This is a big proof on this. It appeared in linear and multilinear algebra. And Kupperton has extended this similar inequality to the subpermanent form. Okay. So instead of permanent, you can take a subpermanent. And then myself and Subramaniam, we extended the result to, for n equal to 4 and 5. Okay, this is the result. This is one of our results. If you take A as a 4 by 4 doubly stochastic matrix and the polynomial has no root in 0, 1, then this Lie-wang conjecture is true on that. So Lie-wang conjecture is true under this condition on that. Okay, this condition is required to see that the inequality is true on. Okay, this is okay. We also try to prove the similar things for n equal to 5. If we take A as 5 cross 5, A is an 5 cross 5 doubly stochastic matrix and satisfies this polynomial. Okay, this polynomial has no root in that. Then this Lie-wang conjecture is true for all alpha belonging. This also is not true for the general interval 1 by 2 to 1. It is only from 0.675 to 1. Okay, this was the. So recently we tried to prove this conjecture. As I told, this conjecture is even open for n equal to 4. N equal to 4 today. We settle this conjecture for n equal to 4. Okay, by using different results and then maximizing and minimizing principle, and then we use it. Okay. For any doubly stochastic matrix of order 4, we settle this conjecture for that. Okay. Not only from alpha belonging to 1 by 2 to 1. In fact, we prove that this alpha or this t can be extended to beyond this 1 by 2 on the 0.48 to that. Okay. This is one of the interesting results which we have recently proved. And then we extended this result to n equal to 6 also, because 4 and 5 is partially proved. This is similar to this the previous result. Okay, and this result was proved. If you take A is an 6 by 6 doubly stochastic matrix, and these polynomials have no root on 0, 1. Okay, then this Lie-wang conjecture is true. Lie-wang conjecture is true for generally true in the interval 0.7836 to 1. Okay, this is more slightly a partial result even for n equal to 6. Okay. But this is one of the well-known conjecture on that. Okay. Still, we are looking to generalize this result for any alpha, okay, or any t in from 1 to 1. Okay, this is one of the progress which we are doing. Now, related to this, as I told, if you look into this, this inequality, okay, this is a convex combination of that. That means if you look into this Wang condition, permanent of TB plus 1 minus T of A less than or equal to T times permanent of P plus 1 minus T of A. This was proved on that. It was proved that this inequality is not true in general. Okay. If it is true, then such a matrix we call as a B. So there are other conjectures related to the bit. What are the stars available and in omega 4, omega 3 has already settled, omega 4, omega 5, another thing. So it's one of the extreme problem on that. So people looking when it can be a constant on that. Okay, so that concept becomes called a mate on that. Okay? So this result is there. Okay? I'm taking a imminent function f chi, whose domain is set of all doubly stochastic matrices. Okay, I take two doubly stochastic matrices A and B. In f chi of Ta plus 1 minus Tb is constant. Okay, and then I say this f chi is imminent function. Okay, this is called imminent mates. A and B are called imminent mates. The logic is f chi is a constant on the line segment containing A and B. Take two points A and B and see that the generalized matrix function or the imminent function is constant in the line segment and A and B. That's a geometrical view on that. Is it possible to find such a and B? So this was supposing proposed by Wang. Okay, this case if you take f chi as I told with a trivial character, then it becomes a determinant mate. If you take this f chi as a permanent, that becomes a permanent mate. So there are two type of mates we have. Determinant mate. Determinant mate is easy. Okay, since enumeration of determinant is easy. So we are interested on permanent mates. You take two doubly stochastic matrix. Permanent of Ta plus 1 minus Tb is constant for all t. Okay, that means permanent value is remain constant in the line segment between A and B. That's a geometric view. Then A and B are called permanental mates. So what are the mates are they? For example, you take these two matrices, A of this kind and B is there. Okay. Then you can check that permanent of Ta plus 1 minus Tb is 1 by 4. Okay, for all values of t. That means these two matrices A and B are mates on the permanental mates. Okay, that means if you fix this, any point between this A and B remain constant in terms of its permanental value. In the case of determinant, if you look into that determinant, you can see that if you take A as a 2 by 2 double stochastic and B also a 2 by 2 double stochastic matrix, then Ta plus 1 minus Tb, which is not constant, is a function of t. Okay, that means in omega 2 you don't have any determinant mates, whereas you can have a permanental mates on omega 2 doesn't. Okay, similarly you can prove that omega 2 has no permanental mates. If you look into this matrix, okay, if you take A as 1 by 2, 1 by 2, 1 by 2, direct sum 1, and J is, as I told, J3 is 1 by 3, 1 by 3. Then you can find the determinant. That means A and J3 are determinant mates. Whereas if you find the permanent, A and J3 are not permanent mates. Okay. So related to that, then as I told, the Wang and Werner and people have started looking on what are the mates in omega n. Okay. What are the different types? Wang tried to do there is infinitely many permanent mates in omega n. And he proved that Jn does not have the mate on that. And Werner I try to find the direct sum of mates when it becomes permanent mates on that. Gibson proved that this matrix x1 minus x1 minus x direct sum 1 does not have a mate on it. We prove that if A and B are mates and C and D are permanent mates, then their direct sum also a mate on it. Wang in 90 gave a necessary and sufficient condition of when this two matrices becomes permanent mate on that. Okay. So in the same paper, he proposed a conjecture. This is a well-known conjecture on that. It's called Wang conjecture. He proposed that for n greater than or equal to 3, okay, you take n doubly stochastic matrix of order 4 or more. Any matrix in the interior of omega has no permanent mate. Okay. That means if at all permanent mates are only as permutation matrices and n greater than or equal to 4. So in the interior of omega n, you don't have a permanent mates. Okay. We look this conjecture on that, and then we disprove this conjecture by giving a class of matrices which is an interior of omega n. So we use the perturbation techniques on that. Okay. So I take A as an n by n matrix, a symmetric matrix, and even I define as a small perturbation matrix. Okay. 0 entries in n minus 3 and n minus 3 with a direct sum of 0 minus epsilon, epsilon, epsilon. So epsilon is a very small quantity. So A tilde is A plus epsilon. This A tilde also is belonging to the omega n. Okay, you can choose epsilon. Then this A and A tildes are permanent mates if and only if these conditions are satisfied. So we obtain the necessary and sufficient conditions. From this, we are able to find a class of matrices which satisfies which satisfies the mate condition. That means that the Wang conjecture is not true. So we disprove the conjecture by giving a set of matrices satisfying this condition. Okay, so this is one result we find. Okay, so based on that, there are other interesting results based on the same connexity. There's something called monotonicity conjecture. But this permanent of Tjn plus 1 minus t is monotonically increasing. This is we call as a monotonicity conjecture. And later, Forager has look into that. He says that permanent of Tjn plus 1 minus Ta is less than or equal to. This is called Forager's inequality, which is similar to the monotonicity conjecture on that. Recently, we are also looking this result on proof of this result. Okay. Now, this is my concluding remark. Almost I have 2 minutes time. Okay. This Jn, as far as permanent of a doubly stochastic matrix, okay, second part of it. Jn is an interesting matrix. The entries are 1 by n, 1 by n. And as I told, the Jn is a minimizing matrix. Okay. Permanent at Jn gives the minimum value among all in the doubly stochastic. That was the Van der Waals conjecture. Then later it was proved as a Van der Waals theorem. So the first inequality, J3 is a matrix such that permanent of J3 is always less than or equal to permanent of Tj3 plus 1 minus T and permanent of T for all J. This is true. Now the question we posed it. It's a long back question. So is it true for a general? That means, is it possible to find the doubly stochastic matrices A and B such that minimum of permanent of A and permanent of B less than or equal to permanent of TB plus 1 minus W. That means you take A and B are two matrices and find the line segment between this and find the permanent. This permanent is bounded between the minimum of permanent of A and permanent of B and maximum of permanent of B. Okay. This was able to verify for certain cases, but still this problem is open because it's one of the class problem which discussed in the permanent in terms of its convex combination. Okay. So this results, this open problem and this monotonicity conjecture, Portugal conjecture, Wang conjectures, and then Lie-wang conjectures, and then Bernoulli's inequality, and this Wang inequality. All are related to the convex combination of two W2 matrices in terms, and its permanent value of convex combination of two matrices. So based on that, a lot of conjectures were proposed, and some of them are settled, some of them still is open on. Okay, for example, the Fourier inequality, Lie-wang conjectures, monotonicity conjectures are still open on. Okay. These are my references. Okay, thank you. I think I finished time. Yeah, I'm happy to answer.
Thank you, Professor Sundaram. Any questions? Okay, so there is no question in that case. Just I request all of you to unmute yourself and thanks the speaker by clapping first.
Thank you, Darnay sir, for talk on that. Okay.
So,
if you have a doubt, I think I already mentioned my mail ID. Probably you can write us. We'll discuss it. Okay. This is a long and problem which we have been working on. That.
Yeah. So for the next talk for this series, we will be meeting on the next Wednesday, same time. And, yeah. So we are done.